Hello, welcome back to Networks and Cybersecurity. We're finishing up on the network compression homework today, and then we're going to move on to cryptography if we have time and there aren't any questions. So, taking a couple days on this homework because a lot of folks struggled with it, and because I think this is a very important concept for network programmers to know. How do you reduce the amount of traffic that your application is using? That is a very important thing to know. Now, internet's being a little bit spotty in my area today, so I might cut in and out occasionally. Apologize for that. Not much I can do, though. Alright, I have to find where I put this thing in my other machine here. There we go. Okay, let's preclude this first with why are we doing this. So remember that we decided to do this because when we were running it on the VM, I'm going to open the VM here in a sec actually and get on there, and we can play with it as well and see if it's improved. But when we were doing this through the VM, if you'll recall, we had a problem. Once there were more than so many people, it started to get slow, or I couldn't handle it anymore. The drawing wouldn't update as quickly. And that's the only reason that we're doing this. So I want to caution you again about not optimizing prematurely, especially network traffic like this, which is hard to optimize. As you've seen, it can be very difficult to do. So the approach that I used originally, serializing the object, sending it, deserializing it on the other end, the advantage to that is that it was easy, right? It was really easy. It was like 10 lines of code long, and I think it was probably pretty straightforward to understand that we just sent the color array over. That is definitely a lot easier than what we're going to do today, what most of you did for the homework. So doing this is only worth it if you have a problem that you already need to solve. So generally speaking, you don't want to put too much stock into your network traffic prioritization. That said, you don't want to go crazy from the get-go. You do want to keep in the back of your mind the fact that network traffic is somewhat precious, especially if you are developing something for web use and you think that a lot of your users will be mobile. So a mobile app or a web app, at that point I would encourage you to prioritize your network traffic right from the beginning, because those devices have data caps, right? And you don't want to make people use up all of their data cap on your application. So when it comes to prioritizing network traffic for a desktop application, I would say don't do it till you have to. And when it comes to prioritizing for a mobile or web application, I would say you should start relatively early on, but don't go crazy with it like we're going to do here until it becomes a problem. So there are definitely levels of craziness. That said, what we're going to do here today is we are going to take this 7,500 byte array that we made, and we are going to zip it into a smaller size. That's basically what we're going to do. We're going to use one of Java's many built-in zipping algorithms. And there's not that many, but we're going to use one of them. Maybe we'll use two if time permits. And this is not particularly difficult to do, so go ahead and implement it if you think that it will be to your advantage. And this is also what most of the web does already. So, well, I don't know about most, but a lot of the web does already. So many websites back in the day, even as recently as, let's say, 5 years ago, they would send you the entire contents of the web page when you access them. Today, most websites, when you come to them, they send you a compressed version, and then your browser decompresses it on their end. So this kind of zipping of the website has already become a very common thing to do. And it is definitely an improvement in how the web is used, as pages have grown massive, especially in the number of images and such that they keep on there. There's definitely tons and tons of dynamic content and videos and stuff on web pages, and this has helped tremendously. Okay, so I have loaded up my Eclipse in the VM. I am going to copy the server over there, and then I'll try to connect to it. So I'll be right back for a second. Okay, we're most of the way there. I'm still moving some files over, but I'm almost there, so come back in here. And I just need to make a folder and move everything in there. You might ask why I don't just export a jar. I bet that if I tried to copy a jar onto this thing, it would complain about security. So, since this is a networks and cybersecurity course, I should mention, generally speaking, it's frowned upon to send jars over the internet to one another, unless you're very confident in the sender's, trustworthiness. And it's not that I don't trust you guys, it's that you might not realize that your system is compromised for whatever reason. And if you send a jar, nasty things can get attached to it, and then nasty things happen to the receiving system. So don't open jars from locations where you're not sure. Okay, it's running, so I'm going to give you my address, and you can connect, and then we will all see how many simultaneous connections we can support now. So I am 143, 105, 165, 12. Let's see if we've improved the number of simultaneous connections that we're able to take. So I've already got one from 90, and I'm not going to launch the client here to save a little bit of resources, so I'll just let you guys do the drawing. And I'm going to try to make this small and move everything over to the side. Uh-oh. Oh boy. VM busy. Okay. And I'm also going to remove my face here so I'm not using up too much of the Eclipse menu. Okay. Gotta make Eclipse a little bit smaller to accommodate. Go right about there. That seems good. Okay, I did this. Look at our size. Doesn't seem to be exceeding in the 47500 range. It looks like the worst size we've had so far was somewhere in the 600 range. Remember, it only updates once a second from our panel. It made the panel the same way here. All right. So first, let's look at compression using the inflator and deflator. Inflator and deflator. So inflation is basically the same thing as decompression. Deflation is basically the same thing as compression. If you've ever used 7-zip, WinZip, any of those, they will use inflation and deflation synonymously with compression and decompression. There's probably some technical distinction between those two terms, but they're usually used interchangeably, so I consider them interchangeable. Now, we did stop before we built this 7500 byte array, so we do need to finish this. We had this as bytes array with 7500 spots in it. To hold all of them, we got the base index, which was the number of rows that have elapsed times how big a row is, times the number of bytes in every individual cell, plus how many bytes are in every individual cell, times how many columns we've gotten to so far. That brings us to the location of the red. Now we need to actually map those things into the array, which means the red, green, and blue, those are all just one apart from one another. So we have base index plus 0. We have as the first one, that's going to be the red, so I did the plus 0 here to differentiate it from the plus 1 and plus 2 I'm going to do later on. We're going to cast it as a byte, and remember I said that if you're dealing with a simple integer that's less than 255, I gave this as a hint in the Discord, if you just cast it as a byte, it'll work it out. Okay, so the bytes that we're trying to get are the last few digits of the integer. So the integer, remember, is 4 bytes big, and we just want the very last one. Well, when you cast an integer as a byte, or when you cast an integer as a byte like this, it will by default just take those that last byte, those last 8 bits, which is exactly what we're looking for. We'll see we have to do a little bit something special on the receiving end because Java treats leading ones as a negative number. That was another suggestion that I gave you, that on the receiving end you would have to do something a little extra. Alright, so that maps the red, greens, and the blues into our array. We now have all of the values in a byte array. Now let's try to make it as small as possible. So I'm going to use the deflator in order to make a new array of bytes. So for that I need a byte output stream. Call this byte stream. And by the way, our file size has gone up to 857, the largest we've had so far, but drawing still seems pretty smooth. I'm not seeing a ton of activity, but it looks like everybody's still drawing pretty well whenever I do see some drawing. Okay, so I've created a new byte array output stream to hold the result when I am done here, and then I'm going to create a deflator, which is going to deflate this deflator output stream. So only a couple of people managed to find these two approaches, but the folks that did also won the large bonus for the, what do you call it, the large bonus anyway. For getting it the most compressed, because these were definitely the most compressed options if you did it this way. Let me see, what did I spell wrong here? There we go. Well, I'll just copy and paste it, who knows. I do hate typing these complicated ones. I don't think anybody beat the thousands range using the manual approach, and we can see here still that the key size has not exceeded 1,000, which is very, very small considering there are so many different colors on the screen. The best anybody got with the manual approach was somewhere around 3,000. So, as with anything else that deals in bytes, you usually have to nest it inside of a try and catch. I'll just let it do this for me automatically. So to use the deflator is relatively straightforward. You're going to write the array of bytes that you want to write. That's going to be this as bytes array here. It'll write it to the output stream as whatever the compressed version of it is, and then we're going to call finish when we're done. This is the equivalent of calling flush. If you don't call finish, then it's not going to wrap it up. You're just going to get stuck on that right line forever, I believe. Okay, so we have written everything to the byte stream. Now we need to get the output of the byte stream here. So I'm just going to call that byte out. And that's going to be byte stream dot, and then we're just going to do, I believe, to byte array. And that will give us the result. And that's it for the deflation aspect. Okay, so now we have successfully compressed these bytes down. And if I print this, now this is going to crash because I haven't actually done the inflation end, the other end. I haven't done the client side of it yet. So this is going to crash, but I am going to see how long it is before it does. Okay, we got 30, in the 200s as I try to draw on the screen. So very, very small indeed, and you can see that echoed in the finished product over there, that even with a very complicated drawing, we're under 1,000 bytes. All right, so I've got the output done. Now let me go back and do the reverse. So I'm going to delete the comment there because that's not accurate anymore. I'll have to rewrite that later. And now we have to figure out how to do all of this process in reverse. All right, so let's copy this whole thing at first, and then we are going to figure out how to reverse it, because deserializing it is going to be very similar than serializing. I'm going to leave this repaint in there. Okay, first of all, we don't take an array of colors anymore. Now we take an array of bytes. I'll just call this, let's call it bytes. I think I already used in as the name for the buffered reader earlier. I don't want to be confusing. So I'm going to call it bytes. We still need to say how many bytes per cell we have, but now we need to do this part first. We need to do all the inflation before we try to process it back into colors. So this is going to go first instead of second. Now instead of a output stream, we're going to have an input stream. We still need the byte array output stream because that is going to be the result of our deflator. But it's actually a little bit different for deflation and inflation. We call the encrypting end or the compressing end the deflator. The decompressing end is the inflator. They're both actually outputs. So this is an inflator output stream. I know it's a little confusing. There is also a deflator input stream, which makes this even more confusing to work with. But what did I get wrong here? It's an inflator output stream. Oh, inflator has an E in it. Those Tor words are hard to spell. Okay, so this is going to be, rather than being a deflator, it's going to be an inflator, and we're still writing on the byte stream that we got. Okay, and now instead of inflator.write, it's instead of deflator.write, it's simply inflator.write, and we're writing on that same array of bytes that we got from our output, which was actually sent to us over the network. So remember, these are two different ends. This is the sending end over the network. This has received it after it's gone over the TCP and everything, so it's coming in on the other end. Other than that, basically the same thing. So I will just change this to in, I guess, instead of out to be less confusing. And there we go. We've gotten it back. So we've done all of the compression through just these two blocks of code here. We've done the compressing it on the sending end and decompressing it on the receiving end through these two relatively complicated blocks of code. But again, you just had to basically find these on the internet somewhere. There might even be an example in your book. Okay, so now the conversion back into an array of colors from an array of bytes. So it's still going to go through rows and columns. We could go through the array of bytes instead, but I'm going to go through the rows and columns and find the right spot in the byte array and map it into colors, because I already had this base index calculated and I can figure that out easily. So these three are no longer going to be used, but we're still going to use that base index. So I know where the red is at. It's going to be at in of base index plus 0 again, just like it was last time. Now, how do I convert it into a positive number? Because as I mentioned in the hint, if you just try to convert the byte like this directly, so remember in is a byte array, I'm trying to cast that as an int, it's going to assume that that's between negative 127 and 127 by default in Java. That's how it does that byte conversion. If I want to get the positive number version of it, I have to do this. I have to do and 0xff. And the reason is pretty straightforward, okay? So when a byte gets converted to an integer, I'll put this as a comment. When a byte gets converted as an integer, Java thinks that it's this, okay? And XX is your byte's value, the last byte value. So for some reason, when a byte gets converted into an integer, Java appends a bunch of ones to it at the beginning. So it makes the first 3 bytes ones. And that's the signal for a negative number. Now when you do and 0xFF, well, 0xFF is this. Okay, which means it's all ones on the last byte, all zeros everywhere else. FF and 0, 0, obviously 0. 1 and 0 is 0. So the first 3 bytes get zeroed out. And then the last byte stays the same, because if there was a 1, 1 and 1 makes 1. If there wasn't a 1, so if there was a 0, then you keep that 0. So the last byte stays the same. The others all get zeroed out. That turns it into a positive number in Java. Positive numbers have leading zeros. So that's it. If you didn't understand that, that's fine. All you have to know is that to convert from a unsigned byte, or from a signed byte to an unsigned byte, you do and 0xFF when you're doing the integer conversion. All right, we're going to do the same for green and blue. Green, blue. Maybe +1, +2. And now we just have to update the color of that spot in the grid. So we're going to go grid of row and column is going to be that color. It's a new color with that R, G, and B. And that should do it. Now we do have to make a couple of other changes somewhere because we've changed the input and output of these two functions. So we have to go back to the client, for example, and the client currently gets a two-dimensional array of colors here, and it gets it from object_in.readObject. And on the sending end, on the TCP worker, it sends the byte array as object_out.writeObject. Both of those use serialization and deserialization respectively in order to write it. Now remember, there's an overhead to using serialization. So what we really want to do is get rid of the serialization completely. We don't need that anymore. We can now just send a raw stream of bytes, a raw array of bytes. I'm just going to comment it out completely. We're going to knock out any references that it has, because we don't need it anymore. And instead of out, we are just going to do our regular old output stream, this one, the socket.getOutput stream, nothing fancy there, and we are just going to write to that. So it's going to be out.write. Probably have to save. Yep. All right. So just plain old out.write. On the client end, same thing. We're going to get rid of the input object stream. We're just going to read a plain old array of bytes. So I don't need this anymore. I don't need, well, I am going to need receive input, but I don't need object input stream as an argument anymore. Don't need that. Don't need that argument. Don't need that argument. Okay. And on the receiving end, I'm going to get an array of bytes instead of an array of color. And that's going to be my socket's input stream in. And then how do I read those 7,500 or so bytes that come in? This was one that was a little bit difficult for people who were using Java 8, because in some cases in Java 8, you don't have all of the functions that you need. In Java 11, and maybe even earlier, maybe in Java 10 or whatever the previous versions were, you could use read all bytes and read n bytes. Those are available to you, and you could simply specify 7,500, or read all bytes is obviously pretty straightforward. We don't have those in Java 8. So I'm going to make this Java 8 compatible. For Java 8, you need to make a buffer that holds how many bytes you're going to read in. Now, based on experimentation here, I see I'm not going over 1,000. So technically, I probably don't need more than like 3,000 or 4,000. It doesn't matter if your buffer is bigger than you need. So I'm going to err on the side of caution, and I'm going to say something big like 20,000. So I'm going to make sure I have plenty of space in case I ever decide to make the grid bigger or something else changes that makes it that I need to support more. So this doesn't have to be exactly the size of your input coming in, just has to be big enough to hold it. Just like for UDP, we made a buffer, and we actually made it 64,000 big, if you'll remember, for UDP. So the biggest that we could send over UDP. We could do the same here, but there's no point in wasting memory when you know you're not going to go over. I mean, I'm not even going over 1,000 here, so there's no point in me going to 64. All right, so in the Java 8 and below, you only have access to this read method, the 3 different versions of the read method, and the correct usage of it, which they have since navigated away from, is to pass the buffer in as an argument here. So let's just rename this to buffer. And this will store the contents being written, the byte array that's coming in from the network, in the buffer. So very similar to how we did it for UDP. And then we're going to deserialize on buffer. All right, and one of the nice advantages here, I don't need class.found anymore because I'm not using an object writer. One of the advantages here is that even though their buffer will have a lot of empty space, like we had to deal with UDP, if you'll recall, we had a buffer that was filled with a bunch of empty space at the end, and when you were trying to decrypt your strings, a lot of you got blanks because they were trying to read the blank spots at the end in that UTF-8 encryption. Well, when we do this deflation and inflation, particularly on this end, the inflation, it's going to get rid of those blanks for us. So when we get to this point here, the in, it's going to have gotten rid of all of the blanks for us, and we'll just have our 7,500 original bytes in this byte array. Okay, so that should be it. I'm going to run this to make sure that everything is working as intended. Let's see. I'm connecting to it. I'm going to do some lovely cyan. I got some lovely cyan there. I'm going to change the size. Lovely. I'm going to change the color. Lovely. Everything updates over there. Now I still haven't gotten the key size and the net traffic to update, so let's go back and fix those. I left myself a little note to do that earlier in the worker here. So I am now able to write the game as an array of bytes. So what I'm going to do here is just get its length and print that out as the keyframe. So I'm going to say bytes to send is the serialized game. I'm going to send that instead, and I'm doing this so I don't call serialized game twice, because calling serialized game is expensive. It's a long process. It requires zipping. I want to reduce overhead. If you call serialized game twice, you are just increasing the amount of processing that has to be done by double there. So I'm updating the keyframe too, and then I'm just going to do the length of that byte array. So let's see if that worked out. All right, when I first start, we see that the traffic is a mere 30 bytes per second, or 30 bytes per frame, which is awesome, right? I asked you to get it under 3,000. We started with 13,000. We're now down at 30. All right, when I start drawing, as you've seen in the in-class version, rarely goes over 1,000. It's pretty difficult to push it over 1,000. It's very hard to tell what kind of images are more chaotic as well, in terms of which one produces the largest file size. It's quite a challenge. With the manual version that most of you did, which is great, the repeating one that I discussed in class, you have sort of the less often repetitions happen, the bigger the file size is going to be. It's not necessarily true of this one. It's definitely a more chaotic and unpredictable in terms of what kind of pictures will reduce it and increase it. Sometimes and the file size actually went down to 425. I'll pick a new color, let's say, and then the file size is going to go up a bit, and then I might draw a couple more parts. It goes up a bit, and then it goes down again, and then it goes up again. You never know what's going to happen because the zip algorithm is a lot more complicated. There's some complex stuff behind the scenes there. All right, so we'll take a poll here, and I'll see if anybody's interested in seeing another approach to complete this. I am disappointed that there are no Pepes in the server panel here. What is your impression of how it runs, too? Does it run better than our Homework 5. Now we only have 6 people connected. I'd like to see us with more. I'd like to see what we can do with like 10 or 20 people connected. Is it still going to work? So if you haven't already, give it a shot. So do you want to see another approach other than the zip version that I've already done? Not the zip necessarily, the inflator and deflator. Alright, people want to see another, and I give the people what they want, so we'll go for one more. I'm going to call this serialized game and deserialized game alt. Okay, I'm going to take another poll. We can do it the manual way that most of you either did or tried to do it, where you counted the number of repetitions and then you stored that in an extra 2 bytes. Or we can do it the zip way, which is competitive in terms of performance with the inflator way. So there's another way to do it using the built-in zip algorithm that is just as good as the inflator and deflator. Or we can try to do it the manual way, where we count the number of bytes. We basically try to compress it ourselves. So zip way or manual way. We'll wait a bit for those results. I would say in this case the manual way was actually the hardest of your options, because if you had looked up how to compress a byte array and just found the code for the other two, I don't think it would have taken too much energy to get it working. Whereas the manual one, you really have to think about it because there's nowhere you can go to look that information up. Our peak network traffic is 210,000 bytes a second at this point, which is still very reasonable. That brings us in the domain of a couple megabytes. Internet connection should be able to handle that. I'm going to add a return here just so I don't have my red line. Alright, it looks like the manual way is the winner. So we're going to try to do it the manual way. I might not do this all the way through just because this takes some time. Alright, for this I am going to copy the same stuff up to the point where I started using the deflator. So that's all the same. I'm still trying to find that base index mathematically, and then I'm going to use my bytes per cell and everything to figure out where it's going to be at in the 7500. So once I've gotten to this point here, I have that as bytes 7500 byte array. So you could have done that and then compressed the one-dimensional byte array, or you could have started directly with the colors and compressed it that way. Let's actually just start directly with the colors and compress it that way. So I think that's probably going to be more interesting. So with this approach, it's hard to tell how big it needs to be. So I'm going to go with the 7500 bytes as my max, but it actually, in the worst case, can turn out to be even larger than 7500 bytes, right? It can turn out to be, you know, if there are no repetitions, it can turn out to be much worse. So I'm going to have to rethink this size later. Rethink the size later, because it's going to have to be larger. Maybe I'll just multiply it by 2 for now and hope that that's big enough. It's probably going to be something you verify by a little bit of experimentation. Now we're going to need at least 5 bytes for every one of our cells in the new array. The bytes per cell concept isn't quite right here. We're actually trying to store our values as a color and then how many times it repeats. So there are 2 options basically when we run into a color cell. If it's the same color we saw previously, then add 1 to some counter. Alright, and then otherwise, we're going to record a new entry in the byte array, and it's going to look like this. It's going to look like the previous color, the count, so repeats so far, and that's going to be probably 2 bytes, remember, because it could be up to 2500. Alright, and that's going to be 3 bytes for the color. And then we have to reset the counter. And start this again. Okay, and then the color that we just saw becomes previous. So that's essentially the process. And on the other end, we're going to complicate it. All right, first we're going to need a last read. And I am going to set those to the value of the red at, what did we call it? Is it grid? Grid of 0, 0. So we're going to start at the very first value there. Last red, last green, last blue. We're going to start at the first color, the one at 0, 0. That means that I also want to start my loops skipping that one. Okay, so how do I skip that one? How do I skip it? Well, the easiest, laziest way, and this is not the way I would recommend, but it's the way I think of now, is if row is 0 and column is 0, then we just skip it, continue. That's the easiest and laziest way I can think of to skip the first cell. So just do that for now. All right, so that skips the very first cell. We have the first cell saved. Now, from that point onward, we follow this algorithm here. So if our color that we just ran into, so if grid of row of column is equal to the previous color that we encountered, come to think of it, I guess I don't need a red, green, and a blue. I can probably just look at color. So let's try that. I think you can do comparisons of color. You should be able to. Let's just stick with this to make sure. So if the color is red is equal to the last red, and same for the okay, then they are the same color, and we have to add 1 to some counter. All right, where should we initialize that counter? Where should we do that? I'm going to start it out here. Counter is 0. Do we start counter off at 0, or do we start counter off at 1? It's actually kind of up to us, right? Depends how we want to counter repetitions. I'm going to start mine off at 1. I think that makes more sense to me. I think when you have 1 occurrence, which is the first tile is obviously going to be the color that it is, that's going to be 1. So when we reset the counter, we're going to reset it to 1. We'll see if that approach bites me later, but I'm going to try that for now. All right, so if the colors are equal, then all we have to do is add 1 to our counter. If they are not equal, then we are ready to save this in the byte array. So that's going to be this portion here. All right, now we do want to keep track of where the next available spot in the byte array is. So we're going to call this the next spot, I guess, value. That'll work for me. Next entry. We're going to start that off at 0, and that's just going to keep track of what the next available spot in the byte array is. We can also do this in multiples of 5, since we're going to have 5 byte values going in there anyway. Alright, so we've got our record a new entry portion in the byte array. So it's going to be that as bytes of next entry. This is if the color doesn't match. So if this color is the same as the previous, add 1 to the colors counter. Color doesn't match, record the previous colors repeat count. As bytes of next entry, first we want to get the redness, so that's going to be the last red. And remember, we can just convert that to a byte. Since it's below 255, that's no problem. And then we're going to do next entry plus plus and repeat that process for the other two colors. Last green, last blue. Okay, so we've repeated that for the final two colors, and now we need to store the location, so the count, which could be up to 2500. So how can we store a 2-byte number, so a number that's up to 2500 in our byte array? What is the best way for us to do that? How do we store a 2-byte integer in our, or an up to 2-byte number in our array of single bytes? Okay, well, I'm going to look it up. Storing an int in 2 bytes, what's the easiest way to do it? My impression is that the easiest way to do it is to just do 2 shifts. 2 shifts of 8 is the easiest way, in my opinion. But, or 1 shift of 8. 1 regular entry and then 1 shift of 8. I believe it would look something like this. I can't quite find it when I look it up, but I believe it would be something like this. It'd be I don't know why I didn't copy that. So I called it the counter. So it would be counter and then shifted by 8 to the right. Yeah. I think that'd be good. All right, and then the last one. So that gives you the next to last byte and then the last byte of counter, which is what we're interested in. We're interested in those last 2 bytes. And on the receiving end, we are going to have to AND this with 0x FF, 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 so 4 Fs on the receiving end in order to convert it back. There are probably cleverer ways to do this. If you can think of a clever way to store the counter, you can put it in either chat. But this is what I'm going to do now. And I think this is right. I might be wrong about the shift here. But that should be it pretty much for storing it in the byte array. Now we just have to do this extra stuff. First we have to reset the counter back to its default value after we've stored it. So the counter goes back to 1. And then we have to make it so that the color we just saw becomes the previous color. And I guess that should be part of this functionality too. So that's going to mean that all of these get updated. And that's going to be pretty much the same thing as here, except it's going to be grid of row of column. Stupid Razer keyboard. Okay. And I'll get rid of the declarations there. Alright, that should be it for the encryption process. Then we should be able to return as bytes when we are finished. I am going to go ahead and test this though, because I'm not super confident in it. And the way I'm going to test it is I am going to try to just print a random byte in the middle and see if it matches something that I expect. I guess that'll probably be a good idea. So let's say After all is done here, I'm going to try to print. It's going to be after the loops here. I'm going to try to print the 5th byte. So I'm going to try to print as bytes of 5 and 0xff. So what should this be? This should be the red value of the second repeating color, right? So spot 0 will be red of first color. Spot 1 will be green of first color. Spot 2 will be blue of first color. 3 and 4 will be location, and that leaves 5 to be the red of the second color that appears. So if this all goes correctly, then I am going to see a red byte proportional to the second color that I expect. And of course it's going to crash immediately because none of the rest of it works. So let's try that out. Let's see. Alright, I'm seeing a lot of crashing. And let's see, I should see a red of 150 after I've made this change. Although it might have crashed too soon for me to actually see it. I definitely don't see it, but I also don't see anything happening anymore, so I think it crashed too soon. Well, that's on the client's end. Yeah, I don't think I'm going to be able to get this to display in that case. I guess I'll have to keep going and find out if it works later. Let me give it one more shot, see if I can draw in red really fast before it goes down. I think I'm getting, oh, yep, alright, I was able to get it in before it went down. So I see that the first red, which is my default red there, is 100. And that's all I was trying to make sure is that I could get the red of the second color that appears, which means at least something is happening. It's not going to be a great example. If I wanted to do a little bit more checking, I would verify that I'm also going to get white after that. So I'll add a space, and then the next color, if there is one, should be white. So it should be in, it's going to be 5, 6, 7, 8, 9, spot 10. I should get a white for the color after that. Try that again. Okay, so I get 100 and then a 255, which indicates a white. So it looks like my repetition thing is working at least somewhat, so I can move on from here. All right. Now on the receiving end, it's going to be pretty much the same stuff. So I'm going to go and keyboard. I'm going to go and copy all of this and reverse it. So I have to loop through, and then the logic is going to be going through the byte array instead. So I'll spell it out here. So I have to loop through the byte array, or I can loop through the rows and columns. We'll see. I don't know what the server says right now. I think it says rip r. Loop through the byte array, and then I have to extract the color, extract the repeats, draw that many repeats into the color array, repeat until no more valid bytes in the byte array. So I'm looping through it, extracting out the color, then the number of repeats, drawing that many, and then repeating until there's no more. Now this is kind of hard to do because I still have a two-dimensional array of color, so it's kind of difficult to extract the number of repeats and map them into it, but I'll see if I can figure it out. Probably not in the one remaining minute here, though, so probably not something we're going to do. But we did the encrypting end, so I will just finish the other end and probably upload it at some point. So the solution I have now doesn't have this manual version. I'll probably wrap it up here and then upload it for you guys. Any other questions before we finish up with the manual version? I know this was pretty complicated, especially when we get into the required shifting in order to store that 2 byte length. That is complicated. Here's another thing that you could have done if you weren't comfortable with shifts. You could have tried to encode the length in terms of two values between 0 and 255 mathematically. And one way you could have done that is with multiplication or something. And another way you could have done it is with subtraction. But the math behind that is not super straightforward. So I think looking up the shift solution would have probably been the easier way to go. Let's see, I think I have one question. How long did it take you? Well, to do the inflation and deflation part, it just took me as long as it takes to look those up. I mean, this part is really straightforward. I think this part you can, well, as you saw, I finished it in about half an hour, the inflation and deflation part. But the other parts, the singleton, all of that stuff was a little bit more difficult. So I would say for me, it'd probably take maybe hour and a half. Just most of it is just looking the stuff up because I don't have any of this inflation and deflation stuff memorized. So finding a source that's not terrible for this stuff took a little bit of time. I also looked up, first I looked that up and I saw gzip. I thought, okay, I'll do it with gzip. Gzip took a lot longer to figure out. That one probably took me like 45 minutes to get it working because it's a lot more annoying syntactically. It's designed for files. So I included both of those examples in my solution because I did the gzip one first, and that one ended up taking me too long, and I thought, all right, this is too complicated. There's got to be a better way. So I did it with inflator, and I was like, yes, that's much easier. So depending on which one you found first, you might have ended up taking a lot longer to do the zipping method. Now, if you tried to do it manually, I would say this is at least, if you get it right the first time, you can be done in a couple hours, but if not, this could take you a significant amount of time. The design on the homework, though, was that if you just did this part here, the encoding it into 7,500 bytes part, so just this part here, I think this shouldn't take more than half an hour, and that part gives you 90% or so of the credit, because this gets you down to 7,500 bytes exactly, which was where you fell in for that 80% of the compression score, because this cuts the size basically in half. Right, so all the other stuff beyond that is just extra. Not extra, but extra in terms of progress. All right, that's it for today. Hopefully I can finish this up for you soon, and I will upload that for you later. If you have any questions about it, feel free to post them in Discord. I will see you guys on Monday, and we will start on cryptography, which might be useful for your next homework. All right, see you Monday.